Target, I can distinguish between acid and base properties. Your acidic properties are things like pH less than 7, the chemical formula have hydrogens, increases the concentration of hydrogen in solution, it tastes sour when you taste it, feels like water, turns blue litmus paper red, it's corrosive to metals, so if you put a metal in there, it will be corroded with the acid, will actually make hydrogen gas bubbles. Base properties, pH greater than 7, it has that hydroxide group, or the ability to decrease the hydrogen in the solution. It feels slippery or like a soap when you touch it. It tastes bitter. Both acids and bases are hazardous, right? Acids, though, are more prevalent in food, while bases are more prevalent in cleaning products. Naming, I can name and write formulas. So the big things to remember about this is if it's a polyatomic, name the polyatomic. It'll either be 8 or ite. 8 will then become ik, and ite will become us. If there's no polyatomic present, then it's straight off the periodic table, hydro something ic acid. And remember, there aren't an unlimited number of these. So off the periodic table, here are your most common: hydrochloric, hydrobromic, hydrofluoric, hydroiodic, and hydrosulfuric acid. So those are all straight off the periodic table, right? Hydro something ic acid. None of the rest have hydro. They all have to do with the formulas. So I'll do the ones on the screen for you. Phosphoric acid came from phosphate, so PO4 minus 3 charge. So then I need 3 hydrogens to balance that out for phosphoric acid. Nitrous acid, nitrous came from nitrite, which is NO2. It's a -1, so you need 1 hydrogen. Hydrofluoric is the hydro from the periodic table, so HF. HCl is hydrochloric acid. H2SO4 is sulfuric acid, because that's the sulfate ion. NO3 is nitrate, so that's nitric acid. And then MgOH2 is magnesium hydroxide. So if you see anything with OH, it's whatever it is hydroxide. Lithium hydroxide, calcium hydroxide, sodium hydroxide, that's all it is, and those are bases. You can recall the definitions of acids and bases. So your areneous acid is one that when you put in water, it dissociates and increases the concentration of hydrogen in solution. Bases, when you put it into solution, it dissociates and increases the concentration of hydroxide, OH. For Bronsted-Lowry, acids still increase the hydrogen because they're hydrogen donors. They release a hydrogen, but bases accept the hydrogens. So bases are hydrogen acceptors. I'm able to identify acid-base conjugate pairs. So this is a question of being able to write chemical equations like what's on the screen and also identify the pairs. So for this one of these things has to act like an acid, one has to act like a base. Since this is the only one with a hydrogen, it's going to transfer the hydrogen over to here. So we're going to have Cn minus left over and HCO3 minus 2. Minus 1 as our new result. So transfer the hydrogen over. So the hydrogen's plus 1, you go down by 1. Since the hydrogen's plus 1, this goes up by 1. Total charge on the left and the right are still the same. And then in terms of looking at this was the acid because it donated the hydrogen. This was the base then because it accepted. All acids will make a conjugate base, and all bases will make a conjugate acid. So they're your acid-base pairs in this case. We also have this interaction, same scenario. This hydrogen will transfer over. It's the only one that has a hydrogen. So this must be my acid, and this must be my base. This will become HCN with the hydrogen transferred over. The other one becomes CO3 minus 2 because it lost a plus. Right? This is now your conjugate acid because it's paired with the base. And this is your conjugate base because it's paired with the acid. Amphoteric, again, just to make sure you understand this, it's a scenario where you can either gain a hydrogen or lose a hydrogen, which means this could either act as an acid or a base depending on the scenario. So if this were to interact with that CN, it would act like an acid to donate the hydrogen over here. If instead this interacted with maybe Well, this is now an acid. It's going to donate its hydrogen to this, and it'll act like a base, gaining one more hydrogen and losing that charge. So this, a hydrogen sulfate ion, can be amphoteric, which means add a hydrogen or lose a hydrogen. It can be an acid or a base. Next one, I understand how water undergoes self-ionization and how this provides a basis for the pH system. Remember, the whole idea is water dissolves itself. Water does not dissolve a lot of itself, right? In a whole 55 moles of water, a whole liter of water, only 1 times 10 to the negative 7 of that 55 moles is ionized, which means the concentration of the hydronium ion and the concentration of hydroxide ion is very, very small when water self-ionizes, but it still self-ionizes. And the pH system then is based on how much in water has ionized, right? If you take the negative log of that 1 times 10 to the negative 7, you get a pH of 7. Water is 7 on the pH scale based on concentration of H and OH. This can be represented in your KW expression. KW, which is always 1 times 10 to the negative 14. This is an always. That equals however many hydroniums there are times how many hydroxides there are. In pure water, each of these will be 10 to the negative 7 based on this. But if I add some acid into solution, that's going to make this go up. This will automatically go down because this number right here, this 1 times 10 to the negative 14, that's a constant. Okay? It cannot change. So there's an equilibrium here between how much H plus and OH minus there is depending on what's in solution. So that's one thing to remember. This is the same as H plus. So now it's a question of utilizing the pH system to determine concentrations. So the first one, if I give you pH, the basic equation is that the negative log of the concentration of H plus gets you pH. But that means 10 to the negative pH can also get you concentration of H plus, depending on what you're solving for. So for that first one, I give you the pH is 3.52. So if I take 10 to the negative 3.52, I get 3.0 times 10 to the negative 4, and that's concentration. So this gets me concentration. Now, is this concentration of hydronium or hydroxide? pH is always having the relationship with H, or hydronium. So this gets me concentration of the hydronium ion or the H plus ion, depending on how you want to write it. And to get hydroxide, there's a bunch of ways to do it. What a lot of you like to do is go, okay, if this is my pH, if I go 14 minus my pH, that gives me my POH of 10.48. So that's my POH. Now if I go 10 to negative POH, that will get me OH out. Okay, so that will get me 3.3 times 10 to the negative 11, and that is concentration of OH. You could have also used KW. So if this is H plus, plug that into KW, you can get OH minus. Doesn't matter which one you do, one or the other. Now that problem didn't tell me anything about my acid or my base. To get a solution with 3.52, I had to add an acid to the solution. So if I asked you what the concentration of acid was, there would have to be some kind of relationship established, and that's what the second problem does. Okay? Now it tells you I have a concentration of MgOH2, and it's 4.4 times 10 to the negative 6. What's the H plus? What's the OH minus? What's the pH? Your first question should be, when I give you the acid or the base, the actual identity of it, is that a strong acid or is that a weak acid? In this case, it's a base. So is it a strong base or a weak base? This is a strong base. And what that tells me is I have complete dissociation. When MgOH2 is put in solution, all of it will become Mg plus and OH minus. So if I have 4.4 times 10 to the negative 6 of this initially and put that into water, all of it will become Mg and OH. I will have no base left. Okay, so I'll have the same number of Mg ions as the initial because it's a 1-to-1 mole ratio, but I'm going to have 2 times that amount of this OH ion, and that's what we care about. Okay, acid base is all about H plus and OH minus. You're hardly ever calculating anything with other compounds. Okay, so what's my concentration of OH? It's just 2 times what this is. Okay, so my concentration of OH minus for this problem is 8.8 times 10 to the negative 6. And I got that from just multiplying by 2. What's my concentration of H plus? Well, that I can get in one of 2 ways. I can use Kw, or I can go through pH. So since I have to have the pH anyway, maybe I'll do that. If I take the negative log of this number, that will get me POH. So if I take the negative log of any concentration, I can get a P. Since this is OH, I'm going to get POH. To get pH, then, I'm going to go 14 minus POH, and that'll get me pH. So that's my pH. That's one of the questions I have asked. And then what's my concentration of H? Well, 10 to the negative pH will get me H plus. The one check you can give yourself after you've done all these math is, this is a basic solution. I'm putting base in. Is my concentration of hydroxide bigger than my concentration of hydrogen ion? And it should be, right? Because I'm putting base in, so this should be bigger than this, and it is. You can also check your pH. If I know that I'm in a basic solution, my pH should be greater than 7, and it is. So there's lots of ways to check yourself to make sure that in the end your math makes sense. So that was all math if you have a strong base or strong acid. You can assume all the acid or base becomes H or OH because that's how it works. If instead you have a weak acid or a weak base, then you have to use equilibrium to find pH. Essentially, the full concentration of the acid or base did not become H or OH. And you need to know how much H or OH it became to use pH to calculate those types of things. So you'll be given some kind of table like this on the test so that you can pick out the numbers you need to solve. The Ka values that are large up there, if you look, you might notice a pattern that those are all strong acids. Okay, the Ks for strong acids are so big, you don't do an equilibrium for them. They aren't in equilibrium. They made all the product. So I can interpret results from different forms of acid-base indicators. You should know that litmus paper for base turns blue, so red paper turns blue. For acid, blue paper turns red. The biggest thing is that if you use red paper and it stayed red, you can't know if that's an acid or just water, right? You need to see the blue paper turn red to affirm that that was an acid. You need to have all the strong acids and strong bases memorized. Here's the list for you again. You can use the I can break candy canes now Santa to remember those, or some other method if you want to. For the bases then, it's the alkali and alkaline metals with hydroxide added to them. And please remember the appropriate number of hydroxides. For example, if it was calcium is your metal, this would be calcium hydroxide CaOH2. You need 2 hydroxides per 1 calcium. In order to do equations for weak acids and weak bases, you need to be able to write equilibrium expressions so you can get K equals to plug in and solve for your unknown value. So here are 3 examples, writing a Ka for chloric acid, a Ka for the second ionization of carbonic acid, and a Kb. Let's run through each one. So number 1, the Ka for the chloric acid, you need to know what chloric is. Chloric is HClO3 because that's the chlorate ion. And when that dissociates as an acid, your acid is hydrogen donor. So you'll have your hydrogen come off and have your chlorate ion left behind. So Ka will equal the products divided by the reactants, just like that. And now for a calculation, I know the concentrations of these 2 things will be the same because as this dissociates, it'll make equal numbers of these. But they will not necessarily equal the amount of acid that was present because of the K. K tells me how much. The bigger K is, the more of these I have per amount of this. Like I said, for acids that completely dissociate, the K is huge because you only have these 2 things and none of this. Now the Ka for the second ionization of carbonic acid, what we're saying here is that you have the hydrogen carbonate ion. So that is 1 hydrogen with carbonate rather than 2. This is the second ionization. It already ionized 1 time to lose 1 H. Now it's ionizing the second time to use the second H. So the K now is still equal products over reactants, just like this. Now one thing to remember, you can do these with water. The change, if I think about this acid in water, is that I add water It becomes a hydronium ion instead of hydrogen, so this becomes hydronium. You don't include the water because it's a liquid. This still equals the same as the H. It's just another way of writing it if you want to. And for bases, you have to react them with water, because without the water, it can't be a base that adds or accepts hydrogens. So you have to have a source of hydrogens for the base. And you can see the water donating a hydrogen to the ammonia to become the ammonium ion and the hydroxide ion. Kb is still products over reactants, and no water because the water is a liquid. So those are just equilibrium expressions, which one of the learning targets says you need to be able to do. So you have a problem where you simply have to be able to write one of these. The next one is being able to do calculations for weak acids and weak bases. So now I have a problem where I give you the pH, and I ask you the concentration of the acid. Acetic acid is a weak acid. If this were a strong acid, you could go 10 to the negative 3.6, and with the concentration of H, you could figure out the concentration of acid because the acid completely dissociates. Because it's a weak acid and the acid does not completely dissociate, you need to use a K value. Once the acid has dissolved, there is an equilibrium between the acid and the H, and the K designates how much that is. So step one for a problem with a weak acid or base is to write that K expression. So here's your Ka, just like we had on the last slides. Now if I take the pH and go 10 to the negative pH, I can get the concentration of H. So there's my concentration of H plus given this relationship. So that is my concentration that goes right there. Now I know these are a 1-to-1, so that concentration also goes right there. I'm looking for the concentration of my acid, so that's my unknown. Give you the value of your Ka. So now it's just a question of solving. 2.5 times 10 to the negative 4 squared divided by that 1.8 times 10 to the negative 5 will give you your concentration of acid. So if you plug all the numbers in correctly, you'll get your concentration of acid is this. This is not a hard problem. It's just a question of remembering this is how you do it for a weak acid or a weak base. You need to have these strong acids and bases memorized to know this is how you do it if it's not a strong acid or base.